Imagine a scenario where two friends, Alice and Bob, wish to communicate a secret message through an unsecure public communication channel. For example, Alice wants to tell her secret to Bob, and she doesn't wish anyone, such as Eve, to be able to intercept and discover the secret. So what is the solution? Alice can convert her secret message into something that is incomprehensible to Eve. This process is called encryption. And the result of the conversion is called the ciphertext. After Bob receives the ciphertext, he will convert it back to Alice's secret. This process is called decryption. In order to do this, Bob will need a key. The field that studies the practice and study of such techniques is called cryptography. There are two major methods that we use in modern cryptography. The first is called symmetric key cryptography. In symmetric key cryptography, Alice and Bob share the same secret key for encrypting and decrypting the message. Another method that we use in modern cryptography is called the public key cryptosystem. Here, Alice and Bob don't use the same secret key as in the symmetric key cryptography. Instead, Bob sends a public key that Alice will use to encrypt her secret. Alice then sends the encrypted message to Bob, who will decrypt it by using his secret key. In order to ensure that an adversary can't crack Bob's public key cryptography uses what is called trapdoor function. This function should be very difficult to solve so that it will take a very long time for an adversary to steal the secret. Cryptography is now facing a challenge from quantum computer technology, as Shor's algorithm is known to solve factoring and discrete logarithm problems, which are the most common trapdoor functions used in current public key cryptosystem. Hence, post-quantum cryptography is born to answer this challenge. Currently, research in post-quantum cryptography is focused on the following approaches. Lattice-based cryptography, which involves lattice in the construction of the schemes. The security of lattice-based cryptography is based on the assumption that several lattice problems, such as learning with errors, are hard. Code-based cryptography, which rely on error-correcting codes. Hash-based cryptography, which security is based on hash functions. This approach is so far limited to signature schemes such as Merkle signature scheme. Supersingular elliptic curve isogeny, which rely on the properties of supersingular elliptic curves and supersingular isogeny graphs to replace Diffie-Hellman key exchange. And multivariate cryptography, which is based on the difficulty to solve systems of multivariate equations. In 2016, the U.S. National Institute of Standards and Technology, or NIST, announced a competition for standardization of post-quantum public key cryptography. 69 proposals were submitted in the first evaluation stage. On January 2019, NIST announced that 26 proposals made into the second round, in which 17 are for public key encryption and 9 are for digital signature. The next stage of evaluation is expected to take 12 to 18 months, after which there may be a third round before the official standard algorithms are chosen. Why does it take so long to choose the winner? Well, doing cryptanalysis are hard and cannot be rushed. Researchers are also still developing quantum-based techniques for doing cryptanalysis on the proposed cryptosystems. And no one knows for sure what a working quantum computer's capabilities will be. So we wouldn't want an easily crackable algorithms being used to protect our password, would we?